to look at factoring difference of two squares, and so this is a special case. So we have to know our perfect squares. Our perfect squares we talked about when we were looking at our radicals. So our perfect squares are a number that you multiply by itself. So 1 times 1, so 1 is a perfect square. 2 times 2, so 4 is a perfect square. 3 times 3, so 9 is a perfect square. 4 times 4, so 16 is a perfect square. So the perfect squares I've listed up here: 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. So that is the perfect squares up to 15. So you might want to memorize those just because they are going to come in to handy when we're talking about the difference of two squares. So the difference of two squares will come into play just because it has to do with a square. The sides are the same, so that means like 2 times 2, the inside is going to be 4, and that is how we get to be a square. Or 3 times 3, which is a square, and the area is 9, so that's what the square means. So two terms, which are perfect squares and are separated by a subtraction sign. So that is super key here. They have to be perfect squares, and they have to be separated by a subtraction sign. That is the rule. Are called the difference of two squares. A difference of two squares can be factored or broken up into two products using the formula a squared minus b squared. And that is going to equal a minus b times the product of a plus b. So you have to have a perfect square, and they have to be separated by a subtraction. So if you do not have a perfect square, and if you do not have the two terms separated by a subtraction, then you do not have the difference of two squares. So if we were to look over here, okay, so this first one. So 1 is a perfect square, x squared is a perfect square, 16 is a perfect square, and they are separated by a subtraction sign. So basically what we're going to do is we're going to take the square root of each one of these, and then I'm going to break it down into two products. You take the square root of x squared, and that's going to be x and x, and then I'm going to have a negative, and I'm going to have a positive. It does not matter if you put the negative first or if you put the positive sign first. The square root of 16 is 4, and the square root of 16 is going to be a positive 4. So it's going to be a plus or minus, because 4 times 4 gives you 16. A negative 4 times a negative 4 gives you 16. All right, looking at this second over here, you ask yourself, is 4 a perfect square? Is x squared a perfect square? Yes, it is. Is 25 a perfect square? Yes, it is. Are these two terms separated by a negative? Yes, it is. The difference of two squares is only going to have two terms, 1 and 2. So what we're going to do, we're going to take the square root of both of these. We're going to write two sets of parentheses, 1, 2. We're going to take the square root of the first one. The square root of 4 is 2. Put a 2 here. The square root of x squared is x and x. And we're going to have a negative and a positive. It does not matter which one you write. And the square root of 25 is a negative 5, and the square root of 25 is a positive 5. If I was to go back in and distribute this 2x to this 2x, this 2x to this positive 5, this negative 5 to this positive 2x, this negative 5 to a positive 5, I would end up with 4x squared minus 25, okay? And so I haven't changed anything. I am just writing 4x squared minus 25 in factored form. Factored means I have two products. So just like we've already talked about when I distribute that. So I'll have 4x squared plus 10x minus 10x minus 25. So these inner terms go away, and I'm left with 4x squared minus 25. Haven't changed anything, haven't changed the value. I'm just going from two individual terms. I'm writing it in factored form, which means I have two products. All right, so I ask myself, is 81 a perfect square? Yes. Is n squared a perfect square? Yes. There is a 1 in front of that, and 1 is a perfect square. Are these two terms separated by a negative? Yes. This is the difference of two squares. So I take the square root of both of these. I have two parentheses. The square root of 81 is 9. Put 9 here. I put a negative and a positive. Take the square root of the n squared, and this is an n and an n. You could write this as n plus 9 and n minus 9. They are the same. All right. So when I first look at this, I ask myself, well, negative 25 is not a perfect square. It is not separated by a negative, but I could rewrite this. The commutative property lets me go in and move these around. Now, 1x squared is a perfect square, 25 is a perfect square, and they are separated by a negative. So I can move these around, take the square root of each one of these, and write my products. Square root of x squared is x and x. The square root of 25 is 5. And I put a negative and a positive. The reason I have a negative and a positive here is because that allows me to get rid of my inners, those two middle terms. Because if you look up here, a positive 10x and a negative 10x, that goes away. That's what happens here. I want those inners and those two inners to go away, and that's what happens. And I'm left with just a negative 25. What is not a difference of two squares? So these are the non-examples. All right, well, right here, this is not subtraction. It doesn't matter if this is a perfect square and this term is a perfect square. This is not subtraction. The first one is a perfect square. It is a subtraction, but 10 is not a perfect square. So this is, even though there are two terms, this is not the difference of two squares. I cannot factor it. I cannot break it down because this last number has to be the same number. They have to be perfect squares. So then you ask yourself, is 2 a perfect square? No, it is not. So this is not a perfect square. Oop, nada, that's not one word. Even if I was to go factor out that 2, I still will get this is not a perfect square, and inside is not a perfect square. And so this is not a perfect square. And that's because I have a double negative. Alrighty. Determine whether the two expressions are equivalent. And so we're going to distribute, or we can go ahead and FOIL. So we're going to have our first, outer, inner, and last. Or we can distribute the 2x to the 2x. And so we're going to have 4x squared. 2x times a negative 3 is going to give me a negative 6x. We're going to go, we went to our first, our outer, our inners, and our last. And we can see that our inner terms go away. And so we have 4x squared minus 9. And so yes, these are similar. They are equivalent. This right here is the difference of two squares. X squared plus 16, we just want to know if they're equivalent. So we're going to go to our first, which is x squared. Our outer, which is a positive 4x. So we went first outer, we're going to our inner, which is 4x, and our last. Combine our like terms, and we have x squared plus 8x plus 16. And so as you can see, these two are not similar. All right, go see if you can see if letter C is similar. Once you go in and distribute or FOIL, you would end up with x squared plus 3x minus 10. And no, they are not equivalent expressions. So the steps to determining whether we can use the distance or the difference of two squares is we always have to factor out the GCF no matter which type of factoring we are doing. We factor out the GCF. We find the value of a and b by taking the square root of each term, and then we are going to use the formula a plus b times a minus b, or if you want to, you can use a minus b times a plus b. It doesn't matter. We write it as a product. But always factor out that GCF. If you do not take out the GCF, if they have one, it will be wrong. All right, example 2, factor each of the following using the difference of two squares formula, if possible. If it is not possible to factor, we're just going to write prime and leave it alone. Okay, so remember our formula is a minus b, a plus b. So this is a squared minus b squared. That is our formula. So you ask yourself, if the difference of if these are both perfect squares, perfect square, and separated by a negative. So we're going to take the square root of each one of these. And so square root of n squared is n. I write a negative and a positive, and the square root of 64 is 8. And that is my answer. Letter B, perfect square. A squared is a perfect square, 49 is a perfect square, and b squared is a perfect square. So I take the square root of both. And I should have said that you look to see, does 81 and 49 have a greatest common factor? They do not. A squared and b squared, they do not have a greatest common factor. And so this will be 9a, separated with a minus and a plus, and then this is going to be 7b and 7b. If you prefer, that is okay. Step 1, you look to see greatest common factor between 25 and 144. Is there one? Greatest common factor between r squared and s squared. So there's nothing you can take out. These are all perfect squares. And so this is going to be 5r and 5r. Notice you have the same number in the same position. This is going to be 12s and 12s. Oh, I'll put a 15. And then this is going to be a minus and a plus. All right, looking at letter D, perfect square, separated with a plus sign. So this is not the difference of two squares. So we cannot factor that. We're going to leave it alone, and we'll write the word prime. We'll have to learn another way to factor that in a few days. X squared minus 10, perfect square, non-perfect square, even though it is separated by a negative, so we cannot factor that, and so we're going to put prime. Difference of two squares, when we go to factor it, has 1, 2 terms. Non-perfect square, this is prime. So this is not separated by a negative, so I can go ahead and switch these around. So then I look to see greatest common factor between 81 and 25 is only going to be 1. And so then these are both perfect squares, so we can take the square root of both of these. The 9's go in the same spot. Make sure that you add the x, and that's going to be 9x minus 5, 9x plus 5. Letter G, you ask yourself, greatest common factor between 9 and 50. So the GCF on this one is 2. So I have to take the 2 out first. So now that becomes 2. When I divide that out, that's going to be 4r squared minus 25. So if you did not take the 2 out, your first thought is that this is a non-perfect square and this is a non-perfect square, and you're probably thinking that is non-factorable. Well, this is factorable by taking out the GCF. That's why we do this. So my GCF is 2. Now I have a perfect square and a perfect square, so I can write that as 2. Take the square root of each one of these, and this is going to be 2r minus 5 times 2r plus 5. So now I have 3 factors. I have 3 products. Looking at letter H, you ask yourself, greatest common factor between 75 and 12. So my GCF is going to be 3. So I take out a 3. When I take out a 3, I'm left with 25x squared minus 4, because this right here does not look like a perfect square. So you would say, oh, that's not factorable. Well, this is. Now I can take the square root of each one of these, and now it's going to be 5x minus 2 and 5x plus 2. So you can take the square root of each one of these. Okay. So looking at this, we always take the greatest common factor. So we're going to go to GCF. And when I divide by 2, my GCF is 2. This becomes 9c squared plus 4d squared. So I can factor this. This is as far as I can factor it. It might not be the difference of 2 squares, but I can factor it. I can make it smaller. I can write it as a product. So I have to go ahead and move these 2 around. So I'm going to have 81 minus r squared s squared. So I can have the subtraction between them. So I switch to get subtraction. And now I can take the square root. And so I have a 9 here and a 9 here, a minus and a plus. And the square root of r squared is r. The square root of s squared is s. So this becomes r and s. The directions are we're going to factor these difference of perfect squares. If the binomial will not factor, write prime. So these are going to be binomials. The difference of 2 squares are binomials, which means that there's 2, 1, 2. So you like to see perfect square, perfect square. There's 2 terms. And so then this can be written as a minus b, a plus b, and that's your answer because you take the square root of each one of these. Looking at letter 3, or number 3, perfect square, but this has a plus sign, and so you would write the word prime because you cannot factor that any further. On number 5, perfect square, separated by a negative, so you take the square root of each. And so you'll have 6 and a 6, a minus and a plus, and an n and an n. Just to refresh your memory that when you are looking at, say, question number 19, so if you have a fraction, you ask yourself, is 1 a perfect square? Is 4 a perfect square? And if they are, you take the square root of the top and you take the square root of the bottom. So yes, 1 is a perfect square and 4 is a perfect square. So the square root of 1/4 is going to be 1/2. So when you write that, you'll have a 1/2 and a 1/2. This becomes an x and an x, a minus and a plus, and then the square root of 9 is 3 and a 3.